I like to talk about some phase diagrams that I found interesting. And I've sent these out so you can get them on email. But so this first one is an example of complete solid solubility. It's copper nickel. The interesting thing here I want to point out is first off, we got complete solubility, so that's going to be our solid solution. In this case, the people that produce the phase diagram call S for solid solution, and why they chose that, I'm not entirely certain. There's an important point here is that when you get these phase diagrams, a lot of times the notation is going to be different than what we taught and what is in a textbook, but you should be able to interpret this in a way that's meaningful. So that's our liquid. This is going to be, say, our alpha phase. This is going to be alpha plus liquid. So again, anytime you want to talk about the composition or the phase fraction, you can do that with a common tangent line. Sorry, a tie line. This diagram has something that I think is actually broken. I made this sheet before I looked at it. I'm not entirely certain what kappa beta means. So this is something that to really understand, we'd have to go back and look in the text. Now, the things that are kind of interesting here, the first is that there's a nickel on the bottom, copper on the top, and the temperature, again, is in degrees Celsius. In this region, we've got a Spinola decomposition. So what's happening is that as we approach 0 Kelvin, we have to approach a situation where there is no entropy. And that's the definition of 0 Kelvin. So here we're at 200 C, still a long ways from 0 Kelvin, but we start seeing this segregation. So in this range, we have a common crystal structure, but the occupancy of that crystal structure is, which I think is probably FCC, is going to be random. And that random occupation of the crystal structure with different species is given by the fractional compositions. But as we get cooler, we're going to wind up with a copper-rich and a nickel-rich lattice. And then if you go all the way down to 0 Kelvin, so we could extend this phase diagram down, at 0 Kelvin, we would have pure copper on the left and pure nickel on the right. This phase diagram below is similar in terms of it's copper gold. Again, you have complete solubility, and now we have several different Spinola decompositions occurring here, and we have a congruent point, and that's something which is different from up here. Now, a congruent point, those typically correspond to something happening in the system. And in this case, it's going to be tied to the ordered phases down here. And the reason that this is any time that you get well, actually, any time that you get a Spinola decomposition or a coherent point in this type of total solubility, that corresponds to a Gibbs free energy curve that's Gibbs energy versus XB. Let's call this AB. That corresponds to the case in which you have a Gibbs curve which has some type of double minimum. And those of you who haven't studied thermodynamics yet, you don't have to worry about this, but what you should know is that this type of shape and this type of shape are tied together, because when you have this type of decomposition, you have a Gibbs curve, which gives you a region of alpha prime, and here's alpha prime plus alpha prime prime. When you have a congruent point such as this, then you have something that will look. So this is our alpha curve. We have alpha, and then we'll have Gibbs free energy of the liquid, and that will give us then regions of alpha, alpha plus liquid, liquid, alpha plus liquid, alpha, which is what you would get if you're drawing a compositional line through there. So these two shapes are tied together. Some things that are noteworthy here is that here we have a temperature scale on the left. On the top and the bottom, we have different scales. So we've got atomic percent on the bottom and weight percent on the top. That's not uncommon. It's worth noting that, see, they are actually fairly nonlinear. So there's not a one-to-one mapping, and that has to do with the difference in the masses between copper and gold. Oftentimes you'll have, say, centigrade on one side and Kelvin or Fahrenheit on the other, but we don't on this diagram. So whenever you are looking at these diagrams, make certain that you are reading from the correct scale. Okay, this is everyone's favorite lead tin eutectic. This is a actually pretty straightforward diagram. We've got the temperature in Celsius. We've got the composition in weight percent. They've actually identified for us all of the relevant compositions and temperatures. So that temperature corresponds to that. That temperature corresponds to that. That temperature is the eutectic temperature. So lead tin is a pretty great diagram, and it's the type of diagram that we like to use in class just because we've got nice big areas that we can look at. It's also actually technologically relevant. If you can look back in history, lead tin, that was one of the alloys that was essential for, well, I guess the rise of civilization. The printing press. The printing press allowed the alloying of these two to make print type that is sufficiently hard that can be used, but at the same time, it also depressed the melting temperatures down to 183. There's no identification here. Well, they don't do a very good job with the phase identification. It's certainly not the way that I would suggest. And typically, instead of calling it PB, we would call this an alpha phase. we call that beta, liquid. And that's because they're solid solutions. So again, just be aware that when you are looking at these phase diagrams, the nomenclature is non-standard, but we assume that you've read enough of these in class to follow them. So let's map this out. So anytime that you have a single phase region, every region that touches it has to have alpha in it. So touches there, alpha, touches here, alpha. Anything that touches beta has to have beta in it. Beta, beta. Anything that touches liquid has to have liquid in it. Plus liquid, plus liquid. So we've identified all of these phase regions, and there are no single phase regions that are touching. Let's come down to this diagram. This is a diagram of magnesium to tin. We've got liquid. We actually have kind of two phase diagrams here that are butted up to each other. We've got one, which is a binary eutectic there, and then we have another binary eutectic here. So let's identify the phase regions. Again, this is temperature in Kelvin and mole fraction tin. They've labeled this region for us. So we know that this is liquid. And there's a two-phase region, which means that this line compound corresponds to SNMG2. And you can see that also by saying, well, there's three atoms, and 1/3 is tin, so that's 0.33. So those correspond to each other. This they're identifying as the line compound tin. BCT is body-centered tetragonal. So it's a line compound, which means that this region is SNBCT plus L, because it's the region which sits between liquid and the body-centered tetragonal. And the place where they touch is this little tiny line right there. And, excuse me, that's our binary eutectic. So that is our eutectic composition, 91%. And that is our eutectic temperature. And it's not marked on this, but it looks like somewhere around, what? Around 475. Okay, now let's look at this next diagram. Okay, some liquid here. We've identified this as magnesium Hcp. That's hexagonal closed packed. We have a two-phase region here, hexagonal closed packed and SNMG2. If this is our magnesium, then that region must be MgHcP plus liquid, and that must make this region SNMG2 plus liquid. And they give us our compositions, and here they give us the temperature. So that's the temperature of the eutectic is 841 Kelvin. Oh, here, sorry. They give our eutectic temperature as 475 for the diagram on the right. So this is another example of a kind of a multi system. So that's binary eutectic, binary eutectic, binary eutectic, binary eutectic, sort of. Up here, there's something else. Let me see. There's something happening up here, and if this diagram were, if this region were something of interest, you would probably see a blow up here, and there would be some blown up version of it in a side diagram or an insert. And I can't really read what's happening there. There has to be some transition, because you see this is liquid plus HCP. So this is hexagonal closed packed. This is yttrium HCP, hexagonal closed packed. This is, they mark it as FCC. That's face center cubic AgFCC. Each of these are line compounds, and you can read off the constituency, and if you needed to, you could go through and you could label these, because you now know that liquid, 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 liquid. You can make these. Up here, there's something else that's happening that we really need to have better resolution on. We have yttrium hexagonal closed packed, and somewhere up here, there's a transition from hexagonal closed packed to body center cubic. And I can't really see it there. So we'll just ignore that little part and hope that whatever we're interested in falls in these regions. This one is a phase diagram. We've got our temperature in Celsius, and they do not tell us what this is, but let's see here. This is a line compound, which is magnesium silicon oxide. On the left is Mg2SiO4. Called, this is forstenite. I have a terrible time pronouncing these. This side is quartz. And this side is another phase that, again, I have a hard time pronouncing. But let's see what this is. This is, if I mix these together, so that means X must be 1/2 in order to get 1 magnesium. which means that I'm adding in Mg Si 1/2 O2 and Y must also be 1/2 in order to get silicon right. So that means Si 1/2 O. So that gives me Mg Si 1O3. So the fact that this is 1/2, 1/2, and this number is not at 50%, that tells me this must be weight percent. Because weight percent and molar percent do not map 1-to-1. Okay, so this is weight percent SiO2 going to the right. So anytime that you get this in the diagrams, you can work out if it's weight percent or molar percent just by using stoichiometric balances like this. This diagram was the simplest paratectic diagram that I could find. Most paratectics are actually fairly complicated systems, and they're all over the place because most phase diagrams are actually fairly complicated, but I wanted something that I could show you. So in this case, ignore the dashed lines. That's from someone's homework assignment. The lines that are important are that. So when I created this diagram, they identified the phases, and the phases are line compounds. We have a phase region here between En and Qz. So and I'm going to draw this in here. Anytime that you start in this range, when you get to low temperature, you have to have En and Qz, which is what makes this little region right here interesting, because in that region, if you were to cool down from Z, you would first form the FO phase and liquid, and then when you cross the paratectic temperature, which is what that looks like around 1575, you would have the FO phase completely reabsorb, because this is En plus liquid, and En phase would come out. And then you keep cooling down, and then you get quartz plus En. And lastly, this is a phase diagram that I think is pretty great. Well, it's great for class. I oftentimes use it for teaching, and that's because it's got interesting features. It's sufficiently complex and technologically relevant that I think people can pay attention to it. We have temperature in Celsius on the left. Here is weight percent nickel, atomic percent nickel. We've got some diagrams here that are some unlabeled phase fields that we can list out here. So let's look at what we've got. So that is alpha phase, and it's actually got a little bit of thickness to it. It's just a little sliver there. So it's actually got a eutectic there. Between these two, this is a line compound. That line compound is Al3Ni, and its atomic percent, so that's a 25 because there's 3 plus 1 is 4, so 1/4 nickel, which puts that at 25%. That line compound then means that this two-phase region is Al plus Al3Ni. This is liquid, which means that this must be Al3Ni, because it touches it. In fact, everything that touches it has it in it. Al3Ni. The liquid touches this, so it's going to be plus liquid. So that's a single phase, which means this must be two phase, which makes this single phase, and this whole region is a solid solution. And they're not marking it with, they're not marking it as a lowercase Greek letter, although they certainly could. But nonetheless, you should recognize it's a single phase. And the way you know it is by counting, right? You've got single phase, double phase, single phase, double phase, single phase, which means this is plus Al3Ni2, single phase, double phase, single phase. This single phase is AlNi. So this is a solid solution. And again, the way you know it's AlNi, 50%, 1-to-1 ratio. So you can look at the atomic percent as a means of identifying what phase region you're in. So if this is single phase, then that means that this little part must be Al3Ni2 plus AlNi. That's a two-phase region. So then, where our Al3Ni2 touches things, for example here, we know we have Al3Ni2, liquid touches that, plus liquid. Our AlNi touches here and here, so that must be AlNi, AlNi. It also touches liquid, plus liquid, plus liquid. The AlNi touches here and touches there. AlNi, AlNi. This is a single phase region, and it's Al3Ni5. That Al3Ni5 here is a paratectoid, because we're going from a two-phase region, this plus something, into a single-phase region. So that's a solid two phases going to one, paratectoid. Single-phase region, this is a single-phase region. Which means this must be AlNi3, AlNi3. That's AlNi3, and they're calling it a gamma prime. So apparently this phase diagram is being used by someone over here. So they've got their named phases, and the rest of this is just kind of filling it in for completeness. So okay, so we've got single phase region, so this must be AlNi plus Al3Ni5. This region touches Al3Ni5, Al3Ni5, and it touches AlNi3. That is our single phase AlNi3. This is a single phase region that is nickel. So it's nickel with a little bit of aluminum in it. So this is going to be the FCC nickel, and it alloys with aluminum. So that's our two-phase region, and they're calling nickel gamma, and they're calling AlNi3 gamma prime. So we'll go with that nomenclature. Okay, so what's happening up here? Well, here's nickel. It's in contact with this region, and liquid's in contact with that region, so that region must be Ni plus L. That is a eutectic, and where this AlNi3 comes up, that little spot must be AlNi3 plus liquid, because it touches AlNi3 and it touches liquid. And if you zoom in here, there's actually a paratectic. So let me highlight there what's happening to try to draw this in. What's happening is that is our gamma prime. So in this region, I have AlNi plus liquid, gamma prime. This is gamma plus gamma prime. This is gamma. This is gamma plus liquid, which makes this gamma prime plus liquid. And that's that little spot right there. And that is a paratectic, and you can just barely see it there. So this is a phase diagram that I like a lot. And it's something that if you go through it after the fact, so we went left to right, we can go back right to left and double check everything, right? Nickel touches this region, so it's nickel plus something. Liquid touches it, liquid. Single phase, two phase, and nickel's gamma, and gamma prime, that's gamma prime. That's AlNi2, single phase. Single phase touches two phase, touches two phase. Both of those have AlNi3, single phase, Al3Ni5, single phase touches two phase, two phase, two phase. So all three of those have Al3Ni5. That region, AlNi, single phase touches here, 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 and here. So all of those have AlNi. Liquid, AlNi and AlNi3, AlNi and Al3Ni5, AlNi and Al3Ni2. So double phase, single phase touches two phase. So Al3Ni2 touches there and touches there. This two phase touches that single phase, which is a line compound. The line compound touches here, here, and here. So Al3Ni, there, and there. In this case, it's in contact with liquid. In this case, it's in contact with Al. This Al3Ni is in contact with liquid. This AlNi is in contact with liquid. So single phase, two phase, single phase, two phase, single phase, two phase, single phase. Two phase, single phase, two phase, single phase. Single phase, two phase, single phase. And here on this far edge, we have Al, and that little zone right there is Al plus liquid. So we've got everything. We went from left to right and right to left, and we verified that no single phase regions are touching except at the special points. And let's look at those. We got a eutectic here. We've got a eutectic here. We have a paratectic here, because we have solid, liquid going to a solid. paratectic here, paratectoid here, because two solid phases going to a single phase, paratectic here, and then this point is a point of congruent melting. So that's why I like this phase diagram. It's got a lot of really interesting features, and it is not too complicated. So this is something that I would really expect you to be able to take this diagram on a quiz, label it, and work with it, and understand the basic functioning of this diagram.